but there is no organizer, right?
When you see, you can say.
Yeah. Yeah, I should write them. Anyway, so we already know what train-track maps are, but I mean, we already have seen that if I have a irreducible outer morphism, then I can always find a representative which is train-track. Okay. So what is good about train-track? So train-track maps are like that. They are always topological representative. More than that, so for any edge E, all the powers of them are tight, right? So we don't worry about the cancellation among the paths. They are already tight. Okay, so today what we are going to do is, I mean, yesterday we already seen a proof, but today we are going to do, I mean, going to take a different way, and which is actually the original proof of Bestevin and Handel, who actually introduced the train-track maps, and they also gave an algorithm how to find them. Okay, but although we have an algorithm, it is not easy to find them because the algorithm actually take a very long way. Okay. Anyway, okay, so we already have defined train-track maps, but I am going to define that in a different way. I mean, it's actually kind of similar, but it's easy to see what is going on behind the geometry. Okay, so suppose I have a group G, finite and what? No, only finite. Okay, so a turn is an unordered pair of edges called, suppose, V1 and V2, such that both of them are actually taking birth from the same edge, like this. So initial of V1 is initial of V2. Okay, that's called a turn. Okay, so if I have a map from G to G, then what I can do, I can define a map TF on any turn. Okay, so I mean, the way Spencer defined them, he actually mentioned to direction. So actually, I mean, in graphs, direction means to edge, right? I mean, that's the only sense of direction. So I mean, here, I mean, in place of direction, I'm just taking two edges. Okay, so TF is, I mean, that's a turn. So suppose I have a turn here. If I apply the F on it, there goes to some edge like that. Okay, my T is going to do, I mean, they are sending this turn onto this turn. I mean, just take the initial two edges of F1 on F of V1 and F of V2. That is again going to define a turn, right? That's a turn, and if I just take only the initial edges of the paths, I mean of the image path, they are again going to define another turn, right? Okay, so obviously there are two kind of turns. One is like that, when my V1 is not equal V2, and another is like that, if I take V1 equal V2. Okay, so obviously those are not the good turns, so I will call them illegal turns. Okay, so a turn is illegal. Okay, a turn V1 V2 is illegal if V1 is equal to V2, right? Okay, so oh, sorry, don't call it illegal. I want to do something. Turn is, call them good if V1 is not equal V2, and bad if V1 is equal to V2. Okay, so a turn is illegal if there exists some n such that Tf whole to the n of V1, V2 is bad. Okay? I mean, what do I mean? Suppose I am taking this turn. So for the first iteration of f, it is going to some nice turn. But maybe in the second one, these two are going to concat. So that's a bad turn, right? That is the difference. So if for the all iteration my turns are going to be good, then I'll call my turn is legal, otherwise illegal. Okay. If a turn is not illegal, it is legal. Okay. Now, so I know what a turn is. Just think it geometrically what is going on. Now let's consider a path. Consider a path. Maybe I call it E1, E2, E3, E4, En. So if I am taking a loop, then my E1 and E2, E1 and En are going to be same. Okay, so inside the path, there are several turns, right? This is one. So if I draw them like this. This is one turn, that is one turn. All of them are turns, right? Two edges. Okay. I will call this path is legal if for all iteration of f, all these turns are going to be legal. Okay. And it is very easy to see. You can just observe it with some example. If that is going to happen, then your f is always going to be tight. Okay, it's just an observation. I don't want to explain that because that is kind of messy. If you do it yourself, I think that's easier to see. Okay, so that's my legal concept of legal path. Okay. And a train-track map. A map. The topological representative Z to Z is called train track if it takes all the if all the path gamma in G is legal in that sense via F. Okay, so that's our definition of train track map. Now we already know the theorem which Spencer mentioned yesterday. If you have a irreducible representative, you are always going to have a train track map for that. So that is our main theorem. Suppose omega is irreducible in outer morphism group of Fn, then there exists a topological representative of O, call it F, such that F is train track. Okay. Moreover,
I'm just confused about the conditions of the train track map. So you said all paths are legal, but not which paths do you want to be legal?
In most schools.
Sorry.
Which paths do you want to be legal again? Can you say it again?
Oh, sorry. I mean, I can actually define. I mean, all the edges are legal. Even I mean, if I take the edges, oh, yeah. Yeah. So, if all, I mean, I can just consider I e to go into z. I mean, those are legal. I mean, that's what I need. I mean, all the edges are going to be tight. Okay. So, if my class is irreducible, then I am going to get a 10-tact representative for that. Moreover, so I am going to come that if so, we have seen that if m of f, okay, so remember that if I have a map from z to z, we can actually consider a matrix which actually represent f such that aij is the number of times the edge ej occur in f of ei, right? We have already defined that in some previous lecture. I mean, so ej doesn't mean in which direction it is. I mean, that map should just pass through ei, and we are just going to count the number, and that will give me a matrix. Okay, so I am talking about that matrix. If m of f is irreducible, then m of f is always it. Okay. Okay. Sorry. Moreover, the representative f for which m of s has the minimal pf eigenvalue. I am going to tell that. I mean, what is that? Is 10-tact, and if lambda is equal 1, then f is just a permutation on edges. Okay. Okay. So what a matrix is? I mean, when we say a matrix is irreducible, suppose I have a matrix. A matrix m equal aij is irreducible if and only if for all aij. Okay, so for all ordered pair I and j, there exists some natural number such that if I consider the ijth entry of m to the that number is greater than 0. Okay, so that is the definition, and we can say that if f is irreducible, then m of f is irreducible. Okay, so that is the definition of a matrix to be irreducible. Okay, so now what is pf eigenvalue? So if I have a matrix which is non-negative, that is all the entries are greater than or equal to 0 and irreducible in that sense, then I am going to get a eigenvector such that all these, I mean, entries are greater than 0. Okay, I am going to get an eigenvector such that all the v1, v2, vn, all of them are greater than 0. Moreover, the eigenvalue corresponding to that is between 1 to infinity. Okay, it's always more than or equal to 1, and it also satisfies some other other important property like, so all the entries of the matrix is always going to less than equal to lambda to the n. So n is the degree of the matrix. Okay, that's the important property we are going to use, and that's all. Okay, so that means for every f, for every irreducible f, I can actually assign a real number, I mean, which is the PF eigenvalue of MF. Okay, that's actually technical. We are going to show, I mean, what we are going to do. Okay, so now to prove that this line is going to be our key. So it says that if I get a representative such that the corresponding eigenvalue, PF eigenvalue, is the minimal one, then it is automatically the train track map. Okay, so what I will do, I will start with a irreducible one. Or algorithm, what is it? Okay, so suppose f z to z is a representative of O and not proper. But irreducible. Okay. So for this one, I mean, I can consider the PF eigenvalue. Okay. Now I am saying that I have an algorithm to construct a new f. Now claim there exists an algorithm such that we can construct another irreducible map f1 from this one, which one we started with, such that the PF eigenvalue of the new one is less than the PF eigenvalue of the first one. Yeah.
What do you mean by proper?
I mean, not train tracks.
Oh, okay. Oh, sorry. Not train tag, sorry. Yeah. Yeah. So I am starting with one irreducible representative and considering that which is not the train tag map, I am going to show that if that is the situation, I can construct a new one which is again irreducible such that the eigenvalue of that is less than the previous one. Okay? And there are two situations that if I consider the irreducible matrix, then all the entries are bounded by lambda to the n, and we know another lemma that if I take a graph whose rank is n and which one has no vertices of degree 0, 1 or 2, then the number of edges is going to be bounded by 3n minus 3. Okay? So I have a bound on my number of edges and I have a bound on my, I mean, value of the each entries. Okay? So there will be only finitely many matrices like that, right? I mean, number of entries is bounded and value of each entry is bounded. So there will be only finitely many of them. So if I iterate this algorithm again and again, eventually I am going to find the matrix which is with the minimal eigenvalue. Okay? So that's my that's the actual proof, and here is the actual, I mean, here is what I have to show, that what is the algorithm. Okay. So that is the important part. Okay. So I start with a z. Suppose that it is not proper. Okay. So what is going to happen? So I will have a turn such that for some iteration, the image will look like something like that, right? I mean, that is a situation where f is not train tag. So these two will first collapse, then it will go in. So what my idea is, because their images are collapsing, I want to do something like that, such that I want to introduce two new edges here, sorry, new vertices here, and I am going to collapse them. Then that will be a valence 1 edge, and I am going to erase that. Okay, so that is my idea. Okay. So actually I don't have much time, but this algorithm has a lot of steps and lot of technical details. So what I'm going to do is suppose E is the edge which is not tight, then there will be an edge like in the image of E, right? I mean, that is the definition of being tight. I mean, this is my C. C and C inverse, I mean, that's a turn, but both of them actually inside the, they're inside the image. Okay? So now what I am going to do is, okay, consider the pre-image of that point, call it star, and consider the pre-image of that point inside my E. So suppose P belongs to E and Fn of P is actually going to star this point. Okay, what I want to do? So this is my P. I want to introduce two vertex here and want to collapse them, right? So there are some technical details which I am not mentioning. We can actually assume that without loss of generality, we can assume that f of P is actually another vertex. Okay? So these arguments actually use the fact that on every graph you can consider a metric space structure, and yeah, you have to use that. So I will use my metric space such that all my edges have the length this, I mean my EI, the edge EI has the length VI here, the IS factor of the eigenvalue here. Okay, so I'm not going to do that. But anyway, I mean, believe me, I can do, I mean, I can assume that my f of P is inside of V, and there exists a neighborhood inside A which actually contain U such that delta of U alpha B with the property f of alpha and f to the L of beta is again inside some, inside the vertex set for some L. Okay? Now what I can do, okay, so I have the property of P that f of P belongs to V. Okay? That means I can subdivide the edge at P. Subdivide the edge at P So that is my edge E, and I can subdivide the edge at my P. Okay. So my graph look like, now I can break that F into edges. Okay. Again, I know that FL to the power alpha, okay, suppose this is my alpha and this is my beta. Okay. FL of alpha that belongs to V, that implies I can subdivide L minus 1. Okay. Subdivide at Fl minus 1 of alpha, and similarly I can subdivide at L minus 1 of beta. Okay. Similarly, just subdivide at all of them. Okay. What does that mean? That means if I go in the back direction, I have all my images f of alpha, f square of alpha, f L of alpha, all are inside the vertex set. Okay? And that will help me to induce a vertex at alpha and induce a vertex at beta with the same logic. Okay? And a situation, another condition here, I can consider if k of alpha, if k of beta are same inside if k of my initial edge. Okay? So inside the edge, suppose that is my fk. So that is fk of alpha, fk of beta. Because I have already subdivided at them, both of them are vertex now, and I have two edges which are going to two edges, and they are actually same inside f of k, because I have considered f of k actually collapse the edge. So it look like that's my image of f of E, that's fk of P, and that is fk of alpha and beta. So now I can collapse them, right? So collapse them, and my new picture will look like something like that. Okay. Now I can see that that's the hanging edge, an edge with valency 1, so I can erase that. Right? Okay. So on this whole process, I mean, where my PF eigenvalue comes. Okay. So whatever I have did, and there is a kind of table. Consider all the group actions like subdividing and what they call it, folding. Folding. So what they act on F. So if F is irreducible, after subdividing it or folding it, I am going to get my F1 is again irreducible. Okay? And the change of eigenvalue is Pf of F is going to be the same of Pf of M1. Okay? And if I perform collapsing plus tightening, then F1 and F2 are both irreducible. That will imply PF of F is greater than PF of F1, and removing valence 1 edge, sorry, valence 1 vertex, again reduce the eigenvalue. Okay. So all I did here, I just used and again first folding and subdividing. So they will keep the eigenvalue same, but after that what I can do, so at the end I have performed a valence 1 homotopy removing, right, and that certainly do what, reduce the eigenvalue. Okay. So my new F which I got from this whole algorithm actually going to reduce my eigenvalue, and if I do it again and again and again, eventually I am going to get the matrix which has the minimal eigenvalue, and that's going to be my 10 tag map. That's it. It's really nice.